In this video, we are going to take a look at section 3.4 on graphing polynomials. The process we will use to graph a polynomial function is the following. First, we will determine if there is any symmetry to the graph. Second, we will find the y-intercept. Third, we will find any possible x-intercepts. And because of this phrasing, I've had to restart the video twice. This is just really poorly written, so I apologize for that. But we want to determine if the graph will cross or touch the x-axis at those x-intercepts. That would be a better way of stating that. So in addition to finding those points, we will also determine the behavior of the graph at those points, and that will help us with graphing. 4, determine the end behavior of the graph. So this is a new concept that we haven't used previously. The first 3 we should be somewhat familiar with because we have used these concepts in the past. So for example, symmetry we talked about in chapter 2. And the 2 types of symmetry that we will be looking for in this section are symmetry to the y-axis, which occurs if we have an even function, and symmetry to the origin, which occurs if we have an odd function. So those were topics discussed in chapter 2. We didn't really do much with them, but we are revisiting them in this section. The y-intercept we talked about how to find previously. We most recently went over it in 3.1, but we also talked about this way back in chapter 1, and it hasn't changed. To find the y-intercept, you plug in 0 for x, and then you solve for y. To find the x-intercepts, that part hasn't changed. That part of step 3 has not changed. You set y equal to 0 and you solve for x. Again, we reviewed that in 3.1. We talked about it way back in chapter 1, and it's still the same thing in this section. But in addition to finding those points, we do have some extra information that we can extract from our equation to help us better draw the graph. And that is whether the graph crosses or touches. And we'll talk more about how to make that determination and then how to apply that knowledge to drawing our graphs. But end behavior is not anything that we've used yet up until this point in the course, and I don't think we're going to use it after this point either. Then, once we've found those 4 things, we will use that information to draw our graph. We'll synthesize it all together to draw the best picture we can of these polynomial functions. You're gonna connect the points using a smooth roller coaster-like curve. So what I'm trying to, the point I'm trying to get across there is that you shouldn't connect the points with straight lines or jagged. There shouldn't be any jagged corners in this graph. It should all be rounded and smooth, like I would imagine a roller coaster might look like, like this. Not sharp angles, but smooth rounded curves, right? Okay, now that being said, we are missing a really important piece of the puzzle when it comes to graphing these functions, and we will not be able to easily find that missing piece of information with the tools that we currently have at our disposal. So based on what we know up until this point in the course, we will not be able to determine what is probably the most important feature of these graphs, which are the tops and bottoms of the roller coaster. So the roller coaster is going to go up, it's going to go down, go back up again. A really important set of points to find in this type of graph is the peaks and the valleys. Like how far up does it go here? How far down is it going to go here before it starts heading back up? These are called local maximums and minimums. And the math that you would need to determine the local maximums and minimums is calculus, at least to determine them directly. You could always guess about where you think they're going to occur, and there's just plot points in that area. You could pick a value of x near that spot, plug it in, get the value for y, and you could plot a point and hope that it's kind of close to the peak or to the valley. But to find it directly and precisely, you would need to use calculus. And we are not going to be introducing calculus at this point in the course. So we are kind of doing these graphs with one hand tied behind our back. We're going to have to try our best to draw the graphs without that really pretty critical piece of information, to at least to make the graphs well drawn and accurate. We're going to have to kind of guess how far up to go here, how far down to go here, and just do the best we can. So without that piece of information. All right, now To determine if an x-intercept crosses or touches the x-axis, we will look at the multiplicity of the root that we need to find that becomes the x-intercept. So when you set y equal to 0, and then you have to solve that equation, you are solving a polynomial equation, which we just talked about doing in 3.3. When you solve a polynomial equation, the answer you get is called a root of that polynomial equation. That root has a multiplicity associated with it. And that multiplicity determines the behavior of the graph at that x-intercept. Right? So if the multiplicity of the root that gives you the x-intercept is odd, then the graph crosses the x-axis at that point, which is probably what you would just automatically assume without any other information. So if you are graphing and you find that, for example, this point here is an x-intercept, you probably naturally assume the graph is crossing through the x-axis at that point. So it might look something like this. Right? And so that's one way the graph can interact with an x-intercept. But it could also just touch. So if the multiplicity of the root that gives you your x-intercept is an even number, so if the multiplicity is 2 or if the multiplicity is 4, the graph touches but does not cross the x-axis at that point. So it's still a point on the graph, but it doesn't cross through. Another way you might describe it is it bounces off the x-axis. So it reaches the x-axis and then heads back in the direction that it came, right? So for example, it could do something like this, right? It could reach that point, I was going to say that value, but that point on the x-axis, and instead of going through, it could bounce back down and head back down like this, right? So this is what it looks like if the graph is only touching the x-axis. This is what it looks like when it's crossing, right? And so we will know the behavior of the graph before we even start plotting points by looking at the multiplicity of the roots that are giving us our x-intercepts. And we're going to, not only can we know that, we need to know that, because without that information, some of these graphs will be really difficult to draw. You won't really know what the shape should look like. The crossing and touching will help us figure out the shape of the graph. All right. For the end behavior, what we're talking about there is once the roller coaster is over, what is the graph going to do? All right, so if you think of the polynomial function, the graph of that as a roller coaster, there's going to be ups and downs, but eventually all of that stops and the graph just takes off in one direction forever. So the interesting part of the graph where the roller coaster is occurring typically happens kind of somewhere in the middle, like right here. But once you get far enough outside of that interesting area, the graph gets really boring. It either just goes up forever or it goes down forever. So it's going to do one of these two things to the right, and it will do a similar thing to the left. It either goes up to the left forever or down to the left forever. So it's going to do one of those two things. Now in the middle, all sorts of interesting things can happen, right? It could be going, it could do something like this. It can go down, back up, down like this, and then maybe it connects back down to there, something like that, right? But the end behavior is not concerned with the roller coaster part. It's concerned with this part right here. And it turns out you can determine the end behavior of these roller coasters by looking at two things from the equation. The first thing is the degree of the polynomial. And what matters about the degree is whether it's an even or odd number. So if the degree is even, like if the degree is 2 or if the degree is 4, the degree is even, you'll have one set of behaviors. If the degree is odd, like 3 or 5, you'll have another set of behaviors. And we will further distinguish the behavior of the graph by looking at the leading coefficient, which is the coefficient of the highest power of x. So notice that both of these things that we're looking at are regarding the first term of the polynomial. The degree is the highest power of x. It's usually the first term. The leading coefficient is the coefficient of the highest power of x. So that first term ultimately determines the end behavior of the graph. Right. Now, I have a typo here because I have leading coefficient positive and then leading coefficient positive again. So as is so often the case, when you copy and paste, it's easy to forget to edit the thing you pick, because, it's basically the same thing. I just, one's positive, one's negative, and I forgot to change that word. So I was being lazy, copied this, pasted it down here, and then I forgot to change positive to negative. All right. So whatever your first term is, right? Let's say that's our first term, and then from there we have the rest of our polynomial. This term dominates the rest of the terms. Once x gets large enough. So let's actually have a concrete example. Let's have like x to the third power plus 2x squared minus 5x, plus 2. I don't know. I'm just making up some numbers. All right. Now when x is equal to 1, each of these terms really has equal weight. It doesn't matter that I'm raising this to the third power because that number is so small that even after I raise it to the third power, it's still a small number. And so this term contributes just as much as this term does, or just as much as this one, right? So when I plug in 1, I get 1 to the third power plus 2 times 1 squared minus 5 times 1 plus 2. And you can see that, in fact, this minus 5 has a big impact on this result, right? Because we're going to get 1, and in fact, we're going to get 0. It's weird. Plus 2 minus 5 plus 2 ends up giving me 0, right? But each term kind of contributes the same, level to the answer, right? Now, contrast that if I were to plug in the number 10, right? So if once I start choosing larger values of x, then this first term becomes really large, because when you take bigger numbers and raise them to higher powers, you get really big results relative to like this term, which isn't really going to go anywhere, right? So if I choose x equals 10, this becomes 10 to the third power, which is 1,000. And that's much bigger than any of the other numbers I'm going to get from these terms, right? Plugging in 10 here gives me 10 squared, which is 100, times 2, which is a pretty big number, but still nowhere near 1,000, right? This is going to give me negative 10 times 5, which is negative 50. And now this is kind of wimpy, right? It's not really affecting the outcome in this case. It's not contributing much. And then the plus 2 is like the worst one. It's still stuck, at the same level as it was when we plugged in x equals 1, right? It's the constant term. It's not even going to budge, right? It's always going to equal 2. It's never going to be any bigger or smaller. But x to the third power gets enormous relative to these other terms as we choose larger values of x. So for smaller values of x, they're equally weighted. There's a lot of, I don't know how to say it, pushing and pulling between the terms, right? Which is what makes this roller coaster, right? So they kind of go back and forth, taking turns affecting the answer. But once you choose like x equals 10, this one really determines the answer. These really don't have as much of an impact, right? 1,000 so it's going to really pull the results towards that first term. If I were to plug in like x equals 20, again, it gets even worse, right? This term becomes so much bigger than the rest of them. So it's really this term that ultimately determines how the graph will behave once the numbers get large enough, like 10 or negative 10, right? The x to the third power term takes over the polynomial and makes the other ones look wimpy, right? That's why that first term is all we have to look at to determine the end behavior, right? So if the degree is even, what I think of for that case is x squared. It's a graph that we were supposed to have memorized from chapter 2. I just call it x squared, but what I mean is y equals x squared. And if you have that one still memorized, remember it's a parabola, and notice the behavior of this graph. It goes up to the right and up to the left. So it goes up to the right and up to the left. Whoops. I should put that on the other side. And it also goes up to the left. Okay. That's the end behavior of x squared, which is an even degree, right? The degree there is 2, which is even. That's the end behavior for every polynomial where the degree is even and the leading coefficient is positive. So I don't really memorize this chart. What I always do is think of the simplest example that fits the same description for the end behavior. So if the degree is even and the leading coefficient is positive, the simplest example of a polynomial with those characteristics is y equals x squared. And I know that one. I have that graph memorized. It goes up to the right, up to the left. And so that's the end behavior for any polynomial where the degree is even and the leading coefficient is positive. Up to the right, up to the left. Now, This gets a little confusing because in chapter 2, another thing we talked about was increasing and decreasing, and that's not the language I'm using to describe this, right? Really, this graph is decreasing right here and increasing here. In behavior is not the same thing, right? We're not using that same language. We're not applying that same concept to this description. So the description's a little more informal. It's going up to the right, up to the left. So that's how we're going to describe that informally. Now there is a formal description that we will use that I'm going to introduce in just a second, which I normally I didn't used to. I was like, I'm not going to talk about that because it's really, what the formal description is what you would learn. It's kind of calculus notation type stuff. So again, we're not going to learn calculus in this class, but this class is designed to help students prepare for calculus, right? So some students will take this class and then go on to take trigonometry and go on to take calculus. And we want to make sure that students are prepared for calculus. So we try to introduce a little bit of calculus concepts in this course. Like for example, optimization, like we did in 3.1. Optimization is a big topic in calculus. For the same reason that we're unable to draw these graphs perfectly, because the local maximums and minimums are optimizations. They're maximums and minimums, like we talked about in 3.1. So calculus is very concerned with that concept. And so we try to introduce it a little bit in college algebra, so when they see it again, hopefully it's not as, it's not a foreign concept at that point. All right, anyways, I'm digressing. Now, if the leading coefficient's negative, so what would happen if I took y equals x squared and I made the leading coefficient negative? Well, we know what that negative sign does. It flips the graph over. Again, we learned that in chapter 2, right? It's a reflection. So now it looks like this. So now what is the graph doing? It's going down to the right and it's going down to the left. Again, the degree is even, leading coefficient negative. That in behavior is down to the right and down to the left. All right. Now what some students will remember is if the degree is even, it's the same in both directions. It'll either be both up or both down. And if the leading coefficient is positive, it's both up. If the leading coefficient is down, it's both, I said the wrong thing. If the leading coefficient is negative, it's both down. Down to the left, down to the right. So that's another way. You'll have to come up with your own way of retaining this information so when you take the test, you can figure out what the end behavior should be. All right. For me, I think of the simplest example that fits the description. I visualize that and that tells me the end behavior. But if you want to, find other ways to remember it, there are other methods of trying to remember that. Now, if the degree is odd, I think of a different graph, which I actually did not make you memorize in chapter 2. And that is x to the third power. Y equals x to the third power. And that graph looks like this. And it goes through like that. Okay. And the end behavior for this graph is it goes up to the right, but it goes down to the left. And so here, the degree is odd, the leading coefficient's positive. So any polynomial where the degree is odd and the leading coefficient's positive will have the same end behavior. It's going to go up to the right, and it's going to go down to the left. If I were to put a negative sign in front of that function, it would flip the graph over. It would cause there to be a reflection. So y equals negative x to the third power. I flip the graph over and it looks like this. It's going to go up to the left and down to the right. All right. And so any polynomial with an odd degree and negative leading coefficient would have this same end behavior. It's in the same category. The end behavior would be the same. So it's going to go down to the right. Sorry, my handwriting's getting horrible. And up to the left. Okay. So again, those are informal descriptions for the end behavior for every possible outcome, right? This is all of them, right? And we are describing it in more informal language. Now on the homework, and again, that's the way I used to teach it. I kind of forgot to finish this thought. However, once we move to doing online homework with Math Excel, which might soon become my math lab, the problems on Math Excel use the more formal calculus type description for the end behavior. So it kind of forced us to teach that notation. And it's not that hard to figure out, right? So the way we would describe this in calculus notation would be to say, I'm trying to think I was going to say maybe I could copy this and erase. I'm not really sure the best way of organizing this. I don't think I have enough room right here. But up is, so if you think about up, right, that's this direction here, which is the y variable direction, right? The y-axis goes up or down. And up is positive infinity for y. So if you keep going up forever, you're heading to positive infinity along the y-axis, right? In the y direction. And so the way we would describe that using calculus language is to say up is y going to infinity. And we use arrows to indicate. So y, we would read this as y approaches positive infinity. That means up. So that's how you would translate that. So up becomes y approaches positive infinity because, again, up or down is the y variable direction. Up would be positive, down would be negative. So heading up forever means y is heading towards positive infinity. As going to the right, left and right is the x variable direction, and right is positive infinity. So if we're going to go to the right forever, we're heading to positive infinity for the x variable, right? And so right translates to as x approaches positive infinity. Right? And so that's how you would say this using calculus language. Right? Now I don't know if I want to go through translating all of these. Maybe I can pause the recording and just rewrite the rules with the more formal language, but let's practice one more, see if you got the hang of it, right? What about, let's say this one right here. So how would I describe the end behavior going down to the right using that calculus language? All right, let's do that down here. So down, again, up or down is going to be the y variable. And if we go down forever, that means we're heading to negative infinity, but in the y direction. So that'd be y going to negative infinity or y approaching negative infinity. To the right, again, would be x approaches positive infinity, right? So left and right would be the x variable. Going to the right forever would mean going to positive infinity. And so that's how you would describe that one, right? Let's do one more. Let's do this one. Going down to the left means that y is approaching negative infinity because that's down for the y variable, as left is going to be x approaching negative infinity because that's negative. Going to the left forever would be negative infinity for the x variable in the x direction. Right? And so that would be this one here. Okay, so let me pause the recording. I'm going to duplicate this page, erase all the writing on it, and then I will fill in the table with the end behavior described using this calculus notation. So give me just 1 second to do that. Okay, so here's the same chart, but describing the end behavior using this language of calculus. And here's another good exercise to practice is taking that language of calculus and translating it back to the more informal up, down, left, right. So for example, this one is telling me y goes to negative infinity or y approaches negative infinity. That would be down, right? Because again, y goes up or down. Negative infinity means down. The graph goes down. As x approaches negative infinity, that means to the left. So this is telling me the graph goes down to the left. And the top one tells me that the graph goes up to the right, right? Positive infinity for y is up. Positive infinity for x is to the right. So up to the right. So that's how that would translate. Okay. So let's go ahead and take a look at some examples. So I wanted to get all the concepts out of the way, and then now we just have several examples in a row that we're going to look at, and then we'll be done. All right, so here's a polynomial function. It's already factored, which is helpful. It's more helpful than not helpful, but there are some pieces of information that are more difficult to find when it is factored. So it's really a good thing that it's factored, but it does mean we'll have a little bit of difficulty with certain things. But it really helps with other things, so it's worth it. Anyways, let's just jump into it. Step one, is there any symmetry, right? This is the first thing in the process. If there is symmetry, we'd like to know about it so that when we draw our graph, we can draw it with that symmetry. It also means getting points for free, right? Especially if it's symmetric to the y-axis. For every point on the left side of the y-axis, you get a point for free on the right side of the y-axis. So that can be helpful as well. All right, is there symmetry in this case? Well, that means, we want to check to see if it's even or odd. That's really the only kind of symmetry you need to look for in this section. And the way we tested for symmetry back in chapter 2 was to pick a number, plug it in to the function, and then see the answer that we get, and then plug in the negative of that number, plug it in, and see what answer we get from that. And if the answers end up being the same, whether I plug in the positive or the negative of a given number, then that's an indication that it's even. If I get the same answer but opposite sign, that's an indication that the function is odd. So there's not really a great number to pick here. I was thinking maybe like 18, because 18 minus 17, that's nice. It's 1. That makes the number small for this one. But then when you plug in 18 here, you get a really big number like 35, and squaring that's going to be big. So I think I'm just going to stick with picking 1, right? It's your choice though. Just don't pick 0. That's the only one that you really want to avoid. So, and don't pick 17, because if you pick 17 or negative 17, that zeroes these out. You don't want to plug in 0, and you don't want to get answers that are 0, because then you can't see the signs, right? You can't see if one's positive, one's negative. We need to be able to see the signs, which means we don't want to interact with 0. So 1 checks all those boxes, right? We can plug in 1. 0 is not going to cause us any issues. So let's plug in 1 for x. We get f of 1 equals 1 minus 17 squared times 1 plus 17 squared. Now these are the result's going to be a really big number here no matter what we do. So we're going to get negative 16 squared times 18 squared. And I'm going to have to use my calculator, of course. So negative 16 squared gives me positive 256 times 18 squared gives me 324. Then I have to multiply those together. 324 times 256, I get this big number, 82944. And that's okay. We don't have to do anything with that number. You just need to know what that number is. So f of 1 is equal to 82,944. If these are even, then when I plug in negative 1 for x, I should also get 82,944. If this function is odd, then when I plug in negative 1, I should get negative 82,944. And if I get anything else besides those two outcomes, then it's neither. It's not even or odd. Right? So that's how we test for symmetry. So plug in the same number over here, but opposite sign. I plugged in positive 1 here, so I need to plug in negative 1 over here. Right? So f of negative 1, and that's going to give me negative 1 minus 17, I skipped a 1 there, minus 17 squared times negative 1 plus 17 squared. And then, so what that's going to give me is negative 18 squared times 16 squared. So notice, same two numbers we had over here, but the sign switched, right? Instead of the 16 being negative, now the 18 is negative. But because we're squaring them, it doesn't really matter, right? So negative 18 squared, I don't even need to use my calculator because I know the answers. I have them over here, right? Negative 18 squared will be positive 324 because negative squared always comes out positive. 16 squared will be 256. When I multiply those together, I'll get the same answer, 82,944. So f of negative 1 also equals 82,944. And so that's a strong indication that this is an even function. Right? If you plug in the positive and the negative of the same number, and you get the same answer from your function either way, that's the property of an even function. Now, the reason I'm hesitating to say, oh, that's definitely an even function, is because technically we have to make sure that it would work like that for every number that we could plug in. For x equals 2 and negative 2, I need to get the same answer. For 3 and negative 3, I need to get the same answer. So I, in theory, would have to check every number to make sure it works every time. But you can tell from the setup of the equation that it's going to work out. Because whether we're going to get the same two numbers here every time, no matter what we plug in, like 2 and negative 2, we'll get the same two numbers here that we get over here. Except the signs will flip, but the squaring makes that irrelevant, right? Because whatever one's negative or positive, it doesn't matter. When we square it, they both come out positive. So every time we're going to get the same answer when you plug in the same number, but with opposite sign, right? So we're kind of taking a risk here. It worked this time. I'm going to assume it's going to work every time and that it's an even function, which means that there is symmetry, right? This tells me the function is symmetric to the y-axis. All right, so there is symmetry. It's symmetric to the y-axis. Okay, so that's step one of the process. Determine if there's any symmetry, and we have, and there is. So when it comes time to actually drawing the graph, keep that in mind. It's symmetric to the y-axis. Next, we want to find the y-intercept. All right, so I'm going to rewrite the function down here. F of x equals x minus 17 squared times x plus 17 squared. All right. To find the y-intercept, which is what we're trying to do here, the first step is to plug in 0 for x. So we will get 0 minus 17 squared times 0 plus 17 squared. And then the second step is to solve for y. All right, so we'll get f of 0 equals negative 17 squared times positive 17 squared. And again, it's going to be a really gigantic number. So we are going to end up getting, whoops, typed that in wrong, 83,521. Right. And that's the y value there, right? Oops, I don't want to do that. I want to do this. Okay. And so my y-intercept is, this is the y value. Again, we plugged in 0 for x. And so the point becomes 0, comma, 83,521. That's the y-intercept. It's a crazy big number. My theory for why they picked this equation to give us such a big number is so to make it more difficult for us to graph it on a graphing calculator. So I have a graphing calculator here just by chance. And if I was going to type this function into this calculator to graph it, you wouldn't see anything in the normal window, right? So the normal window of your graph goes from negative 10 to positive 10 for x and for y. That's usually the default setting, right? But the y-intercept here is way beyond 10. And the x-intercepts are at 17. We're about to find those in just a second. And so you wouldn't see the x-intercepts in your normal window. You won't see the y-intercept. So when you actually plug that in and you hit graph, it's just going to be blank. It's going to be a blank screen. So I think they're trying to make it difficult to see the graph in a graphing calculator. That's my theory for why the numbers are chosen the way they are. All right, that's the y-intercept. All right, now we want to find the x-intercepts and whether the graph crosses or touches the x-axis at those intercepts. Okay, so to find the x-intercepts, we take this function and we plug in 0 for y. So remember, f of x is the y variable. So step one is to plug in 0 for y. So we get 0 equals x minus 17. I'm just having trouble writing now for some reason. X minus 17 squared times x plus 17 squared. Right. Here's where having this polynomial factored is a huge help, because plugging in 0 for y and then solving this polynomial equation, you want these to be factored, because once you have it factored, you can get the roots out of the factors, right? So it actually is a big time saver having this polynomial already factored for us. So this is where it's very helpful that these are already factored. Because step two now is solve this for x. Well, since it's already factored, I just set each factor equal to 0, and I solve for x, and I get my x-intercepts. And so what we're going to end up finding is we'll add 17 to both sides, and we get x equals 17. So positive 17 is one x-intercept. Solve this one by subtracting 17 from both sides, and we'll get x equals negative 17. So that's my other x-intercept. To write those as points, as ordered pairs, so again, we set y equal to 0 here. So as an ordered pair, this would be 17 comma 0. That's 1 point. The other point would be negative 17 comma 0. So that's my other x-intercept. So there's two. There's two x-intercepts. But in addition to having these 2 points, we can also determine what the graph is going to do at those points by looking at the multiplicity for these roots that gave us these points, right? So the roots of this equation are x equals 17 and x equals negative 17. These two roots lead to these two x-intercepts, but these are the roots, right? Those roots have a multiplicity. We talked about multiplicity in the previous section, 3.3. The shortcut to determining the multiplicity is to look at exponents of those factors. So as long as you're using exponents to write your repeated factors, the exponent on the factors will be the multiplicity for those roots. So this root comes from this factor. Sorry, I'm saying the answer. This factor has an exponent of 2, which means this root has a multiplicity of 2. Right. Same thing here, right? This root was derived from this factor, which had an exponent of 2, so the multiplicity of this root is 2. And so if the multiplicity is even, so it doesn't even really matter what that number is, it just matters whether it's even or odd, right? This is an even number, and so if the multiplicity is even, then the graph touches the x-axis at that point. It bounces off of it, right? It doesn't cross through the x-axis, it reaches it and then heads back in the direction that it came. Either from below, or it could be from above. It could reach the x-axis from above, that becomes the x-intercept, and then it heads back up in the direction that it came from, right? Same thing's going to happen here, right? This is an even number. Sorry, I kind of mixed up I meant to make the colors contrast a little better. I didn't really do a great job here. But that's going to mean that this one also touches the x-axis. It doesn't cross through. Right. So not only do we have a couple of points, we know what the graph should be doing in the area, in the vicinity of those points. All right. The last thing that we want to find is the end behavior. So maybe I'll do that over here. And then we'll try to put this all together to get our graph. Right. So the step 4 of the process is to find the end behavior. Because this was factored, it actually makes it a little more difficult to find the end behavior. Because the end behavior is all based on the leading term. We want to know the degree of the polynomial, and we want to know the leading coefficient. Those two things will tell me the end behavior of the graph. What does it do once the roller coaster is over? Does it go up forever? Does it go down forever? To the left and to the right? All those questions can be answered by the degree and the leading coefficient. But it's factored. So remember, the degree is the highest power of x. But with it being factored, it's kind of hard to tell what that would be. So, and this is kind of hard for some students. I've tried to explain it, and I've looked at eyes of confusion as I explain this in my class. They're just like, I have no idea what you're talking about here. What you might have to do in a case like this where it's already factored is to multiply it back out. But I'm kind of lazy. Like I don't want to multiply it out completely with all the details that go along with that, because that's going to be a lot of work. I don't really care what it multiplies out to. I only care what the first term would be when I multiply it out. That's all I want to know, right? And so I just track the first term. I don't like track all the details of when I multiply these together. I just track the first term of all the details. And then the first term tells me the end behavior. Well, I'm skipping ahead. The first term tells me the degree and the leading coefficient, which will tell me the end behavior, right? So x minus 17 squared means we have x minus 17 times x minus 17, which I would have to FOIL, right? Because squared means you multiply it to itself twice. You have to FOIL. I'm not going to bother with f, o, I, and l. I'm just going to look at f, the first term, right? Because that's the one that matters for the end behavior. So when I FOIL this, I'll get x times x, which is x squared, and then some other stuff, which I'm just not going to bother finding the detail of. And that's where I lose students. They look at me like, okay, you lost me. I don't know what you mean by this. The first term will be x squared, and yes, there will be some other terms. There will be negative 17x, another negative 7, if you go the rest of the FOIL process. But those terms are not going to tell us anything about the end behavior. So I don't really need to pay attention to them. So I just do x squared and don't really bother with finding out what the rest of that's going to be, right? And then I have to do the same thing with this one, right? X plus 17 squared would be x plus 17 times x plus 17. I would have to FOIL those out, right? Multiply these two together, FOIL. But I'm not going to bother with all those details. I'm just going to look at f. multiplying the first two terms together, which again would give me x squared and some other things, right? If I continued the FOIL process, but I only care about that first term. So I'm going to ignore the rest of those details. And then these would have to get multiplied together, right? And what would happen here is we would have x squared times x squared, which gives me x to the fourth power. And some other details would follow that, right? If I had these details here, those would have to get multiplied together. And I get some other stuff to go along with that x to the fourth power. But I don't care about that other stuff for the end behavior. I only care about that first term because that will tell me the degree. So the highest power of x that I'm going to end up with here is 4. So the degree is 4. And the leading coefficient is just a 1, right? It's just going to be positive 1. And I don't need the other details. So just focus on the highest power of x all the way through that when you're multiplying it out, because that's all you need to look at for the end behavior. The other terms don't matter. Okay. Now, if that bothers you, what I tell students is if you don't like this, if it's confusing or it doesn't make sense to you, then just fill in all the details. Put minus 17x here, minus 17x plus whatever 17 times 17 is, 289. Right? It's fine. It's not wrong to do that. It's just going to take you some extra time to get to that result. And you're going to get the same result I just got here, right? But it's going to take you twice as long if you have to fill in all those details. But it's not bad. I'm not trying to make you feel bad about that. It's just a matter of like saving time, right? This problem's already a pretty lengthy problem. We look for ways to save a little bit of time. So that's a way you can save some time. But it's more important to be right than it is to be quick, right? So in order to get the answer right, you feel like you need to fill in all the details there, then you should do that. It's not wrong to do that. Take the time to make sure you're going to get the answer right. Okay, so now that we have the degree, what matters, again, kind of like the crossing and touching, what matters here is not so much what that number is, but whether it's even or odd. In this case, the degree is an even number. So there it glitched on me. So I was talking about this in my last video. I noticed one time that when it glitched on me when I wrote, the audio glitched at the same time. So if that's happening, again, I apologize for that if the audio just glitched. All right. The degree is even, right? That's all I care about, whether it's even or odd. And for the leading coefficient, I don't really care what that number is. What matters about that is whether it's positive or negative. And it's positive this time. So the degree is even, the leading coefficient is positive. That will tell you the end behavior of the graph. Now you have to be able to, draw a conclusion from this on the test, which might mean that you have to memorize this chart here. Or I know this is just looks like scary just seeing it pop up on the screen, but just this part of it right here, right? So if you have to memorize that chart, that's what you have to do. But I think it's difficult because it's all the same words in different combinations. So it might be hard to remember which one goes with which, right? Up, right, up, left, up, right, down, left. It sounds like the cheat code for, a Nintendo game. I don't know if you guys, I'm old enough to remember this. It was for Contra, where it was up, up, down, down, left, right. We knew that cheat, and that gave you like infinite life or like a bunch of life or something like that. I can't remember how many lives it gave you, and like weapons and stuff. So it was like a common cheat code that everybody knew. Anyways, that's what this starts to sound like. And it might be hard to remember the order and where everything goes. If you try to memorize this, it's a lot of the same symbols, just in different type configurations, right? Just slightly different configurations each time. So if you're just memorizing without really understanding, it's easy to scramble these up and you'll get the wrong thing. What I do is I just remember, I don't even remember, I just think, what's the simplest example of a polynomial with an even degree and a positive leading coefficient? And that's x squared, right? Y equals x squared. The degree is even, the leading coefficient is positive, and I know what that graph looks like. This end behavior, the graphs aren't going to look the same, but the end behaviors will be the same, right? Whatever the end behavior for this graph is, it'll be the same end behavior for this because they're in the same category, right? And so the end behavior here is it goes up to the left and it goes up to the right. And so that is what my function will do, right? So if that's what it does for x squared, that's what it's going to do for x minus 17 squared times y plus 17 squared, because they are in the same category when it comes to end behavior. right? So it'll be up to the left, up to the right. If you have to address this using calculus language, again, you can like I remember it this way, or I just kind of translate it from the graph that way using the informal language. And then from this, I translate it into the calculus notation. Up is again the y direction. And because it's up instead of down, it's going to be positive infinity. And left is the x direction. Left is towards negative infinity. So, and I forgot the arrow there. Right? So that's how that would translate back into the calculus notation. Right? For this one, up, again, is y going to positive infinity. To the right is x going to positive infinity. Right? So that's how I would describe that in behavior in the language of calculus. All right, so now we have all this information. We want to put it together to draw this graph. Right? And so let's make some space here for that. So here's the y-axis. Here's the x-axis. Hopefully that's enough room for all the numbers we need. Again, these were big numbers, so I'm going to have to kind of skip ahead by choosing a scale that allows me to jump to the number that I need, basically. So the origin's still going to be 0, 0, but I need to get to 17 on the x-axis. I don't want to get there by going by ones. 1, 2, 3, 4, 5, 6. It's gonna be a lot of marks. It might take up a lot of space. I might run out of room. I'm going to go by 5s, right? So 5, 10, 15, 20, 17 is going to be about right here, right? A little bit more than 15, right? So that's 17, 0. We also have, as you can see on the screen, negative 17, 0. So 5, 10, 15, 20, right? Except this is in the negative direction. So negative 17 is going to be about right here, right? So those are, my spacing doesn't look quite right. This looks a little bit closer than this one does. So sorry about that. But this is what my x-intercepts look like. My y-intercept, I'm not even going to bother scaling here. It's such a gigantic, maybe I should, but it's 80,000 and something, right? What was it exactly? I can't even remember. Way over here. 83,521. So if I'm going to scale this, I got to go by like 20,000s. I think that's minimum. So if I'm going to scale this on the y-axis, we're going to have, sorry, I forgot what I was doing there for a second, 20,000, 40,000, 60,000, 80,000, 100,000, excuse me. So 20K, right? 40, whoops, I skipped ahead a little bit too much. This would be, let's just skip here. This is going to be 80,000, right? This is going to be 40,000 right here. Right? And this is 100,000 up here. So 83,000 is going to be pretty close to the 80,000 mark. I should use different colors for the points here. So let's make these blue. And this one's going to be just a shade above 80,000. So about right there. And that's it. So if you go, we did a lot of work, but we only found 3 points from all that work that we did. Right? We found 1 y-intercept, 2 x-intercepts. And if that's all you use to try to draw this graph, you will get the wrong idea of what the graph looks like. So if I don't consider the end behavior, if I don't consider whether it crosses or touches, then with just these 3 points as my guide, I would guess that the graph looks something like a giant U, right? It's going to look something like this. And I might think, oh, the graph looks like it's doing, if I connect those 3 points in the simplest way possible, this is what I would think the graph looks like. And that's actually pretty far from the truth. So that's why we need the end behavior. Notice the end behavior is that the graph should go, is right up here, right? The end behavior is the graph should go up to the left and up to the right. And that is not what I drew here, right? This graph is going down to the left and down to the right. So what I drew does not match the end behavior that I determined from the equation. So I need that end behavior to tell me what this graph looks like, because the points alone will not be enough information. All right, so let's undo that graph. The graph should be going up to the left, according to this. So ultimately, once this roller coaster is over, the graph should be heading up as I go to the left and also up as I go to the right. So it should be heading up this way. So if I start with that in mind, so let's just start from the left-hand side here, right? The graph's going up as it goes to the left. As it's coming back to the right, it's going to have to reach this point here. And then what is it going to do at that point? So not only did we find this x-intercept, we determined how the graph behaves at that x-intercept. And we found that at negative 17, 0, the graph should only touch the x-axis. It should not cross through. It should bounce off of the x-axis. So what should happen here is instead of heading down through the x-axis down here, it's going to bounce off the x-axis and head back up this way. And then where does it need to go next? The next point it needs to meet up with is the y-intercept, which is this point right here. Now, does it just, does it look like this? This is where calculus would come in handy. Like, should I keep it, should I just level it out to that point? In fact, I don't think that's the case, right? Because we actually, for symmetry, found, oh, sorry, it wasn't what I thought it was. I thought this was like 85,000. So this is 82,000. This is kind of a little bit of a hint what the graph should do. It's a little bit below the y-intercept. So actually, I do think this is what the graph is doing, right? So it's heading up towards the y-intercept, and it just kind of slowly levels out as it reaches there. And then this will be the peak in this area, right? It's not going to go any higher before it reaches the y-axis. But calculus would have helped us know that if we could use some tools from calculus, which we can't because we don't know those, right? So what I'm saying is, how do I know the graph doesn't do something like this? Maybe it does that instead. Maybe it does something more like this. I don't know. Calculus would help me determine that a little bit easier. So I'm just guessing. I'm just guessing that it kind of levels out and reaches the y-intercept as the peak, not the peak. Yeah, the peak of that mountain. Right. Now from here, where is it going to go? Now it has to be symmetric. So whatever drawing I make over here, it should be symmetric to what I end up drawing over here. So once I've kind of made that decision, that kind of makes the decision for what this side's going to have to do, right? So it's going to go kind of level out like this, head down towards the y-intercept here. And then what does it do there? It also touches, right? We found that the graph touches at both x-intercepts. So it will bounce off the x-axis once again, which is perfect because then that matches right back up to the end behavior I was expecting, that it should be going up to the right. Now this is a horrible, horrible draw. I'm really not happy with exactly how this looks. I think I made this top part way too flat. I think it should be a little more rounded there. But ultimately, the shape is a lot more sophisticated than just those 3 points would lead you to believe. Right? It's only with the end behavior and the crossing and touching that we're able to actually put such a complicated shape together with only 3 points to work with. And it's actually a W shape, right? Instead of just like an upside down U shape. And so that's what the graph looks like, roughly. Again, I feel like this is not the best drawing of this function, but I think it's good enough with the information that we were provided. And so I'd be happy with this as your answer on your test, right? It doesn't have to, I can't ask your graphs to look better than what I'm able to do in the lessons that I provide. So if you can draw it at least as well as that, you're in good shape. I'm really just looking for, do you have the intercepts? Do you have the crossing and touching right? Do you have the end behavior right? Do you have the y-intercept? And as long as you're drawing all of that with rounded curves, and again, I kind of didn't do the best rounding here, and not sharp, jagged angles, then you have a good drawing of the graph. I wouldn't be able to ask any more of you. So, all right. So that took a while to get through that example. I'm going to do one more example in full, where we go through all the details like we just did. And then I have 2 more examples in the lesson. And in class, I never do the second 2. Because after you do a couple of them, it just kind of gets repetitive. The second 2 examples really aren't much different than the first 2 that I'm doing. But what I'll do is I will pause my recording and work out the details of those last 2 problems, and then show you the answers so that you can check to see if you did them correctly. So it'll be one of the moments where I ask you to pause the video, do the problem on your own, and then I can show you the answer and you can see if you got it right or not. But let's do this one in full from start to finish on screen, on the recording. All right. So what's different about this one is it's not factored. And also the degree is odd, so that's going to make a different kind of looking graph. So this is different enough from the first one, it's worth doing all the way through. 1, is there any symmetry? This time there's not. But we can test for it by choosing, let's go with 1 again. We'll plug that in. We get f of 1 equals 1 to the 3rd power minus 3 times 1 squared. I'll skip the details on that work. It's going to be negative 2. Right, so f of 1 is negative 2. If it's an even function, when I plug in negative 1 for x, I should also get negative 2 as my answer. That would indicate that it's even. If it's an odd function, I would expect to get positive 2 when I plug negative 1 in to the function. If I get anything different than -2 or +2, then it's neither. And if it's neither, there's no symmetry. Right? So let's see what happens. We plug in -1 for x. We get -1 to the third power minus 3 times -1 squared. That's going to be -1 plus, not plus, it'll be minus 3, right? Because -1 squared will be +1. -3 times 1 is -3. And that gives me -4. Right? So it's neither, right? I don't get -2, I don't get +2. So it's not even, it's not odd, it's neither. You also maybe could have determined that using the shortcut we talked about in chapter 2, which is if it's a polynomial that's not factored. This is why you might say, why didn't we use this shortcut in the last one? It was factored. That kept us from using this shortcut I'm about to talk about. But if it's a polynomial that's, written like a normal polynomial like this, if all the powers are odd, it's an odd function. If all the powers are even, it's an even function, and constant terms count as an even power. If it's mixed, like this one is, we have a power of 3, we have a power of 2, that's a mix of even and odd, it will be neither. So that's another way you maybe could have determined that, which means there's no symmetry. I hate to say there is no symmetry because maybe there's some kind of symmetry, but it's not one of the ones that we can detect, right? So no symmetry. No symmetry that we're aware of. Okay, so I find the symmetry step of this process to probably be the least fruitful. It takes time to determine, and most of the time there won't be symmetry anyways, but it's something that we're asked to do, so that's why I make sure to do it. Now, for the y-intercept, step 2, let's find the y-intercept. We plug in 0 for x, so we'll have 0 to the third power minus 3 times 0 squared, which is going to give me 0 minus 0, which is going to give me 0. Right. So step 2 of the y-intercept process is solve for y. Again, this is our y variable here, and we just get 0. And so I plugged in 0 for x, I got 0 for y, so my y-intercept is 0, 0. Right. That's the y-intercept. And it's boring. You get a point, nothing, there's no new information, there's no crossing or touching that goes along with that. It's just a point, 0, 0. Now, let's find the x-intercepts. This is more interesting, right? And so for the x-intercept, we're going to set y equal to 0. Let's pick a different color to kind of change things up here. Maybe not red, since that's right here. Remember, f of x is the y variable. I'm going to plug 0 in for that. So I'm going to get 0 equals x to the third power minus 3x squared. And then I have to solve that equation. And that's what makes this interesting. So this is step 1. Step 2, solve this for x. It's a polynomial equation. Now, we talked about solving polynomial equations in 3.3. That's, again, solving this means we're finding the roots of this equation. And sometimes we saw in 3.3, finding the roots requires that we do P's and Q's and use synthetic division. Now, I was nice to myself here by choosing this example where we wouldn't have to do that. The other way of finding the roots is to factor it. In the last example, it was already factored for us. So again, that was kind of a gift to myself, like, hey, this problem's already factored. We don't have to do any work there. This one is easy enough to factor, but I do think there might be 1 or 2 homework problems where when you get to this point, this won't be an easy thing to factor. You will only be able to find the roots by doing the P's and the Q's, finding your list of possible roots, and then using synthetic division to check them. And once you find a remainder of 0, then you can stop and factor. That might have to be done on 1 or 2 of these problems, so just keep that in mind. But this one, we can just factor it without doing the P's and Q's stuff, right? So we can factor out the x squared, that's the common factor here, and that leaves me with x minus 3. And so that was all there was to that. And then we solve it by setting each factor equal to 0. We get x equals 0 as one solution. X minus 3 equals 0 means we get x equals 3 as the other solution. So these are my roots to this equation, which means they are my x-intercepts on my graph, right? So these roots, they're really interesting. And so we've seen them in several, contexts. In 3.2, we call them zeros of the polynomial. In 3.3, we call them roots of the equation. In 3.4, they are my x-intercepts. It's the same set of numbers, right? This 0 and 3, those are the zeros to my polynomial. those are the roots to my polynomial equation. They are my x-intercepts. It's the same, they're the same thing, same set of numbers in slightly different context, right? So my x-intercepts will be, because again, y was 0, right? So I'll get 0, 0 as one of my x-intercepts, and I will get 3, 0 as another x-intercept. Let's try that again. It'll look like a sigma. All right. Okay, and that'll be my other x-intercept. Now, in addition to finding those points, we can also determine whether the graph is crossing or touching at those points by looking at the multiplicity here. So the multiplicity of this root is 2. Because the exponent was 2, the multiplicity is 2. That's an even multiplicity, which means the graph will touch the x-axis at that point. Just like in the last problem we saw. Multiplicity is even. If it's an even number, the graph will touch. All right. Now this one, though, this factor only occurs once. The exponent here is an invisible 1, right? So there's no exponent there at all. That means the multiplicity is 1. All right. If the multiplicity is 1, that is an odd number. 1 is considered an odd number, which means the graph crosses the x-axis at that point. So the graph will touch the x-axis at 0, 0, and it will cross through the x-axis at 3, 0. All right, that's the x-intercepts. Let's look at the end behavior. This one's going to be a little bit easier to jump into because it wasn't factored ahead of time. I have the polynomial multiplied out, so this is step 4. Right? And the end behavior is based on the degree of the polynomial, which I can immediately see in the function I was given. The highest power is 3. And the leading coefficient, which is a 1. Right? There's a 1 in front of this x to the third power. So the degree is 3. The leading coefficient is 1. Right? And so the degree is equal to 3. The leading coefficient, I should scroll down a little bit more. Whoops. Leading coefficient is equal to 1. And again, what I really care about regarding these numbers is for the degree, I only care if it's even or odd. I mean, I care about it more than that for other things we're doing in the problem, but for the end behavior, all we really care about the degree is whether it's even or odd. That's going to tell us the end behavior. And for the leading coefficient, again, it matters what that's equal to, but for the end behavior, all that matters is whether it's positive or negative. And this time it's positive. Right? Again, we can go back to our chart, look it up on the chart, but on the test, you'll have to have some way of drawing this conclusion about the end behavior. And you can try to memorize that chart, but that's, again, it's easy to scramble up. What is, I think, a better approach is to think of what is the simplest example that fits this same description. And the simplest example, this actually isn't the simplest one, but I just like to use this one. The simplest one is really y equals x to the first power. That's also an odd degree. And that one you should know. It's just a straight line that does this. But I feel like because it's a straight line, I don't like it. It's just not interesting enough. And so I prefer x to the third power. But it's the same end behavior for both of them, right? What's happening here is it's going to go up to the right, and it's going to go down to the left. Right? Even if you want to use this one, it's the same thing, right? Up to the right, down to the left. So either way is fine. In calculus notation, this would be y goes to infinity as x goes to infinity. That's the up to the right. This one would be y goes to negative infinity, and I forgot the negative sign. Negative infinity as x goes to negative infinity. Right? So that's how you would describe that using calculus notation. All right, so this is my end behavior for x to the third power. It's the same end behavior for this function because it fits in the same category. All right, so now let's put all that information together that we have. We'll do that over here, I suppose. So here's the y-axis, here's the x-axis. This time we don't have such crazy big numbers to deal with. We have the point 0, 0. That's the y-intercept, but also that was an x-intercept, right? 0, 0 is both on the x and y-axis. So it's both an x-intercept and a y-intercept at the same time. It's the only point that can be both at the same time. Right? But then we also have this y-intercept here of 3, 0. So 1, 2, 3. We have this point right here. All right. And you know what? If you think about all the work we just did, those are the only 2 points that we found in all of that work. It's just 2 points, which again, if that's all you were going by, would never be enough information to figure out a complex pattern, right? There's no way to tell what this roller coaster looks like with just these 2 points. But with the end behavior and the crossing and touching, we can actually figure out the more complex shape that's at play here, right? So remember, the end behavior was the graph should go down to the left, which means ultimately once this roller coaster is over, it's heading down to the left and up to the right. That's ultimately what the graph should end up doing. So let's start from down here. It's going down to the left. The first stop it has to make is this y-intercept here, which is also the x-intercept, where it will touch the x-axis, right? It won't cross through, it only touches, so it's going to bounce off the x-axis back down. And I feel like I'm not really happy with that. Let's try to redraw this whole thing. Undo. Okay. Oh man, I made a lot of little marks there. Okay. So again, up to the right, down to the left. It's going to go up. I'm doing a horrible job of drawing here. Let's start from here. It's going to do like this. There we go. All right. And then it's going to touch and head back. Oh, it still feels like I'm making a little jagged point there. Should be a rounded, smooth curve. That's what I'm really trying to illustrate here. And it's going to head back down. Now, how far should I head back down? Until I start heading back up to this point, I would need calculus to determine that. That'd be the easiest way to determine it. Now, if it's really bothering you, not knowing if I'm dipping low enough here, choose a value of x in this area, plug it into the function to see what you get for y. I think you'll be surprised, if I'm not mistaken. Well, maybe I am. There's been problems where I've done this, where I'm like, oh, it probably just goes down a little bit, and it's like -20 or something. I'm like, wow, it really goes back down that far. I don't think that's happening on this one, actually. But if you needed to know, you could find out. You could plug either of these values of x, there's 1, there's 2, plug that into the function, get the y value, and that'd give you an idea of how far down you should dip. Now, finding that actual, low point in that valley precisely, and to know that it's the lowest point in that area, you would need to use calculus to do that. Which, by the way, is kind of a sales pitch for calculus. So if that sounds like an interesting thing to you, maybe you should consider taking calculus. It's actually a really great course. It makes math more meaningful because it's more applicable. There's like a purpose to a lot of the stuff that you do in calculus that you just don't really get to see in algebra. So I think, to me, taking calculus helps math just make more sense in general, and maybe shows the value of algebra a little bit better than just stopping after you take algebra. Anyways, we reach this point here where the graph will cross, right? So at 3, 0, we determine that the graph should cross through the x-axis at that point, which is perfect because that lines right up with the end behavior I was expecting. So it's going to cross through here and just take off forever, going up to the right forever. And so that is what this graph should look like. All right, so what we're going to do to end this video is we have 2 more examples, but it's not going to be a long time on this video as far as watching me, explain it. I'm going to pause the recording. I'm going to ask that you pause the video, and then you try to graph this function by finding the symmetry, the y-intercept, the x-intercepts, and the end behavior, and try to graph it. So try to do as much of that as you possibly can on your own. Then resume the video and you'll see the answer to this particular problem. We'll go through it real quick, and then I have one more example where we'll do the same thing. So pause the recording. You pause the video, I pause the recording, and then resume it once you've worked out some of the answers to this problem. All right, so let me take you on a tour of all this work that I just did. So the first thing I looked for was symmetry. There is indeed symmetry in this particular function. It is another even function. And so the graph will be symmetric to the y-axis. I tried to draw it as symmetric as I could when I got to that part of the problem. I determined that symmetry by plugging in 1 and -1, and I noticed I got the same answer either way. I got 80 both times, and so that's an indication it's an even function. For the y-intercept, I plugged in 0 for x. I ended up getting 0 for y, so I get the point 0, 0. Nothing else to say about that one. For the x-intercepts, I set y equal to 0, and then I have to solve this polynomial equation. Again, thankfully, I chose these problems nicely enough that I didn't have to do P's and Q's. I didn't have to do synthetic division. This was factorable. I factored out negative x squared. The x squared minus 81 factors again as x plus 9, x minus 9. And then I set each factor equal to 0. Solve for x in each case. So we get x equals 0, x equals negative 9, x equals positive 9. Those are my three x-intercepts, which give me 0, 0, negative 9, 0, and positive 9, 0. And then we can determine whether the graph crosses or touches at those points. And so here the multiplicity for 0 was 2, right? Because we have an exponent of 2 on that factor. Multiplicity is 2. That's an even number, so it will touch the x-axis at that point. But these both have a multiplicity of 1. And so for these two x-intercepts, the graph will cross the x-axis at those points. For the end behavior, the degree is 4. So we go up to the top, the degree, the highest power is 4. But this time the leading coefficient is negative. That is different than what we had in the previous two problems. And so the end behavior in this case will be down to the left, down to the right. I determined that I didn't draw it on there, but again, with an even degree, I think of y equals x squared. But if I want the leading coefficient to be negative, that's going to take the graph of x squared and flip it over. Right? So it's going to be upside down. So it's going to go down to the left, down to the right. That's how I was able to figure that out. There is the calculus notation that describes the same thing. And whoops, I didn't mean to draw that random straight line through there. And so this is what the graph ends up looking like. So again, you don't get to see me like construct it in real time, but again, the end behavior is down to the left, down to the right. So I kind of started with that idea. And then I plotted these points, negative 9, 0, 0, 0, 9, 0. Those are the x-intercepts, which were really the only points we had. The y-intercept was also 0, 0. So it was just this point again right here. And then going from here, I head up to the first x-intercept. The graph crosses the x-axis at that point. So I cross through. I don't know how far up to go. I don't know where the peak actually occurs. I would need calculus to figure that out. So I just kind of estimated where I thought the peak would happen. And then I have to start heading back down to hit the next point, which is 0, 0, where the graph touches the x-axis. So it bounces off of it back up this way. Again, another peak, symmetric to this one. I tried to draw it symmetric. And then heads back down to the next x-intercept, which is 9, 0. The graph crosses through that, and then it matches up with the end behavior, which is it goes down to the right. And so that's how I came up with that graph. All right, one more example to do, and we'll do the same thing. We will pause the recording. You can pause the video, see if you are able to determine the symmetry, y-intercept, x-intercepts, and end behavior, and put the graph together. See how much of that you can do, and then resume the video to see what your answers should have been. Right. I hate saying it that way because it sounds like I'm assuming your answers are going to be wrong. So what's a good way to say it? I don't know. Resume the video to check your answers. That's probably a better way to say it. All right, sorry about that. So pause the video, try the problem out yourself, then resume to check your answers. Okay, so here's the work I did for this last problem. Symmetry, there wasn't any. I confirmed that by plugging in the number 1 and negative 1, and I got two different answers. They didn't match up in any way that would produce any symmetry. So when I plugged in 1 for x, I got negative 800 for y. For it to be even, I would need to get negative 800 for when I plug in negative 1, but that doesn't happen. And for them to be odd, I would need to get positive 800 here, which also doesn't happen. I actually end up getting 0. So since I don't get 800 or negative 800 over here, then it's neither even nor odd, which means there is no symmetry. All right. For the y-intercept, you plug in 0 for x. You simplify this. This is positive 1. That's positive 1. So 1 times negative 4 is negative 4. So you get 0, negative 4. That's the y-intercept. The x-intercepts, you set y equal to 0. It's already factored for you. So this is where it's beneficial to have it already factored. It makes it that much easier to find your x-intercepts. So I can it's already factored. I don't have to do P's and Q's, synthetic division. I don't have to factor it myself. It's already been factored for me. I just jump right into setting each factor equal to 0, which is what I've done here, and then solving for x. And so we do get a somewhat unfortunate value for the x-intercept, at least one of them. So this one gives me an x-intercept of 1/6. This factor gives me an x-intercept of -3. The multiplicity will tell me whether the graph crosses or touches at these x-intercepts. For 1/6, the multiplicity was 2, because that was the exponent up here, which is an even number, which means the graph will touch at that point. It'll touch the x-axis, but won't cross through. For -1, the multiplicity is 3, because that's the exponent up here. And that's odd. It's an odd number, so the graph will cross the x-axis at that point. This -4, you might be wondering, well, why didn't I do anything with that? Because it doesn't have a variable. It doesn't produce a solution, so it does nothing for finding x-intercepts. You can just ignore it for that exercise. All right, now for the end behavior, try to keep the graph hidden until the end. See, I guess I could do that and you still can't see it. All right, for the end behavior, we need to know the degree and the leading coefficient of this polynomial. Having it factored makes that more difficult. So it makes x-intercepts easier to do. It makes end behavior more difficult to do because I have to figure out, well, what would the highest power of x be if I multiplied this out? And what would the coefficient be for that highest power of x? And so I went through the exercise of writing it out and then imagining if I multiplied all these together, what would the highest power of x end up being? And to do that, I just focus on the first term of every one of these. Because ultimately, when everything gets multiplied to everything else, you'll have one term where it's all the first terms getting multiplied together, and that term will be your highest power of x. So I ignore all the other details. I don't want to waste time multiplying, foiling this out, doing FOI and L, and then having to multiply that to another thing, and then to another thing, and then to another thing, tracking all the details of all that. I really only just care for the end behavior about the highest power of x, and that will be produced when the first terms all get multiplied together. So I took 6x times 6x times x times x times x times the -4, because all of those would get multiplied by -4 eventually, and I came up with this. -144 x to the 5th power, right? There's 5 x's there. And so that would be my highest power of x. There'd be other terms that follow it, but I don't really need to know what those are, right? The degree, the highest power is going to be 5, and the leading coefficient would be -144. So that means the degree is odd, the leading coefficient's negative, and so that tells me the end behavior will be down to the right and up to the left. I got that by thinking of, well, for an odd degree, I think of this graph, x to the 3rd power. It goes up to the right and down to the left. But if I want the leading coefficient to be negative, it flips the graph over. And so now the end behavior becomes up to the left, down to the right. And that's what I have here. And here's the calculus notation for that. So I take all that information and I plot the points I found. There's only 3 of them that I could find, the 2 x-intercepts and the y-intercept. And they're really kind of close together this time. And so again, with just those 3 points, you might think, oh, it's a parabola. But the end behavior and the crossing and touching give us a much more subtle, I don't know, subtle is not the right word there, but it helps us find that more complex pattern that is occurring with this graph, that the points alone will not help you identify. 3 points would not be enough to really get a good sense of what this graph looks like without additional information. So if you're trying to graph it with just points only, you got to find more than just these 3. All right, so it's going to go up to the left, down to the right. And so I kind of started with this part here. Now here's where having calculus would be a big help. I'm pretty sure, just based on my experience with what these graphs look like, that this graph is not going to go from this x-intercept straight to this y-intercept. It's not like it would just kind of zip over there and then head back up this way. It's going to be more balanced than that. And so I'm expecting the graph to actually dip below the y-intercept for a while. I don't know how low it goes. If I was that curious, I would pick a number for x in this area, like -1/2, and plug it in to see exactly how low that graph might go. Or I would use calculus. It would tell me exactly what x value to use and exactly how low the graph would go before it starts heading back up. You don't need to do all that. We're just estimating. Just so take your best guess. I think it's going to go down a ways first, then head back up. And on its way back up, it would catch that y-intercept. And then it would hit the next x-intercept. And you can't go very far over to hit that x-intercept because like it's at 1/6. It's just a slice over. I don't know how to say it. Just a thin slice over to the right. That's where the x-intercept is located, right? So the y-intercept is at x equals 0. Then the x-intercept is at 1/6. So it's just a hair. That's a good word for it. Just a hair over, right? And then, so going back to this, the end behavior is it goes up to the left. So starting from there, we cross this x-intercept, head down a ways. On our way back up, we catch the y-intercept. Then we hit the next x-intercept where it touches. So it will bounce off of that, head back down, which matches up with the end behavior that we're expecting. So this is an idea of what the graph would look like. It's not the most perfectly drawn example of this function, but it has all the correct features that we were interested in finding, right? It has the right x-intercepts, y-intercept, the end behavior is correct. So again, this would be good. And even if you did not know to go down first and then head back up, if you just went straight from here to here, I'm not going to count that against you because again, you can't know any better without calculus. So that concludes the video on section 3.4, and I'll see you in the next video for section 3.5.